Extended exponential growth and decay. Consider the following scenario. A cup of coffee, initially at 95 degrees Celsius, is cooling in a room with ambient temperature 21 degrees Celsius. Now the cup of coffee is cooling in a negative exponential fashion, and this can be seen on the graph. Now the temperature of the coffee approaches 21 degrees Celsius as time approaches infinity. So in other words, the longer this coffee stays in this room cooling, the closer the temperature of the coffee to 21 degrees Celsius. Now, will the temperature of the coffee ever reach 21 degrees exactly? In theory, no. It'll get very, very close to 21 degrees, but will never equal 21 degrees Celsius. So that's represented by the blue line, which in effect is an asymptote to the curve. Now, we know that in reality, there are other factors at play, and the temperature of the coffee may in fact dip below 21 degrees. So we're just talking in theory here at this point that the temperature of the coffee will never reach 21 degrees, but will get ever so close to it. Now, the simple exponential growth and decay model will need to be extended to allow for this. So this is the formula P equals A multiplied by e to the power of kt is not sufficient to model a situation like this. So the extended exponential growth and decay formula looks something like this. And I've used similar pronumerals to what I've used before. The only change between the extended model and the simple model is the introduction of another constant n. So P equals n plus A times e to the power of kt. So if I took the n out or made n equal to 0, so just remove the n, you then have the simple model. So if n equals 0, then you have the simple exponential growth and decay model. Now at time t equals 0, the value of p, or the initial value of p, is equal to n plus a. So it's the combination of n and a, so the sum of these two values there sets the initial conditions or the initial value. Now this gives rise to three cases depending on this value of k and also the value of a. So case 1, k less than 0, so a negative growth constant, p approaches n as t approaches infinity. And this is because a e to the power of kt approaches 0 as t approaches infinity. So just imagine k is a negative number, t is a really, really big number. So you have an index that's, for example, negative a million or negative a billion. So think of a really, really tiny number. So a negative with a really big number after it. E to the power of that number is very close to 0. So this term effectively becomes 0. So we end up with just p equals n, or p approaching n. And case 1 is like the cup of coffee situation. So p, or t in this case, the temperature of the coffee, is in fact approaching n. N would be the ambient temperature of the room. Now, case 2 and case 3, this is where the growth constant is positive, but the change between, or the difference between these two cases is whether a is greater than 0, or a is positive, or a is negative. So case 2, positive k, positive a, p approaches infinity as t approaches infinity. So it behaves like the simple model in that sense that as t gets really big, p gets really big. And case 3, k positive but a negative, p then approaches negative infinity as t approaches infinity. Now, differentiating this function, this extended exponential growth and decay function, so dp dt, because of course there'll be situations where we're interested to know the rate of change of p with respect to time. That's equal to k times a times e to the power of kt. However, the derivative can be expressed very much or very similar to the way we represent the simple model, but just with a slight change. You notice this a e to the kt here. If you go back to the formula, for the extended exponential growth and decay formula, sorry. If you subtract n from both sides, and in fact I might just write this in here. So p minus n is equal to a e to the kt. We can then express this derivative, okay, or the rate of change of p with respect to time, as k multiplied by p minus n, since p minus n is equal to a times e to the power of kt. So what we can say from this is that dp dt, or the rate of change of p with respect to time or with respect to t, is proportional to the difference between p and n. So again, if we go back to the cup of coffee example, the further away the curve is from the dotted line, the steeper, or at least in the negative direction, the steeper the gradient. So it's almost like the blue line is pulling p towards it. So the further away the curve is, or the function is, from the blue line, it's like the blue line's acting like a magnet, drawing it toward itself. But then as the curve gets closer to the blue line, that magnetic pull sort of weakens, and then it starts to shallow out. So this is the difference we're talking about. Okay, so just think of it this way. The bigger the gap between the curve and the blue line, the greater dp dt, or at least the magnitude of dp dt, whether it's positive or negative.